The thing really is obviously fatigue, and particularly fatigue in aerospace. This is a typical bonded flying surface, that's old-fashioned now because it's aluminium to an aluminium core, adhesively bonded. If you look out for the plane at 10,000 meters, 95% of all those flying surfaces are glued. There's not one mechanical fastening. So have another gin and tonic, it's a good idea at times. So it's all glued. These days, of course, it's more likely to be carbon fibre skins and a Nomex, that's impregnated paper with phenolic honeycomb. But there are problems from time to time. This is a rather famous aircraft, now retired. You probably recognise the Concorde, and it had 2 or 3 failures like this. This was not an Anglo-French design argument here. It came in and it had lost the rudder section due to fatigue. Of course, there is a backup of the second rudder section. So it does occur, we do get fatigue failures, and probably more in military aircraft at times. They're flying harder and faster than the civil ones, but it is a real problem. The classic way of determining this, we've heard, is, for example, to do your Instron, get your Instron machine. This is a tapered double cantilever beam. We've seen DC beams. This is often used for metals. Aluminium, the blue is the adhesive layer. Run a crack down here. Linear elastic fracture mechanics. We can determine the maximum G, energy release rate, from this. Obviously, P min gives us the minimum value, so we can get the range of energy release rates, simply calculated from linear elastic fracture mechanics. We also know G1 max, of course, so we can run this test, measure the rate of crack growth per cycle, plot it against the range of strain G release rates, or G1 max, by analogy to the Paris law equation, and that's what we and others have done for many years. But we've recently been asking whether this is correct. Are these the correct parameters to use? That's the range of energy release rates, or G max, to actually do the plots, and maybe then to go on to do things like fatigue prediction, or is it very misleading? So it's a quick bit of theory. The very well known, the Paris equations, is what the metals community do. We have the Paris law here. Delta K is the range of stress intensity factor, of course, largely developed empirically by Paul Paris, which we're honoured obviously to have at this conference. And, so it really makes the conference extra special with Paul here. It's mainly empirical, but at the time, actually, if you go back to the original work, there was some theory behind it using Krakow displacement, and much more recently, there's been various atomistic modelling studies. Not sure I always believe them, but if you do believe them, they come out with the Paris law for materials like ceramic. So there is some evidence, theoretical evidence, that it's correct. And also, as we heard in the very first talk, if you apply this to metals, the Paris law, you get the correct material dependency on parameters like R ratio. So the metals people are very happy with the Paris law stress intensity factors. The problem is with adhesive joint stress intensity factors are usually invalid. Therefore, we work with energy release rates. But remember that K squared equals EG is the modulus, and G is our energy release rate. And therefore, if we simply use delta G, this is not the same thing as using the Paris law, clearly. And we've heard this in several talks. K is proportional to root G, therefore we should not use the range delta G if we're thinking we're similitude or analogy to the Paris equation. And obviously using G1 max is also not the same thing as the Paris law in terms of stress intensity factors. So following on from the Paris-Irwin paper of 65, the elegant work, again done by the University of Delft group, they argued that similitude to the Paris law equation, you should use this equation for your plots. This is root delta G, where this is obviously the square root of G1 max, this is the square root of G1 min. It follows obviously from this proportionality, and G1 max square, and we'll be using the term delta root G as the analogy and the similitude to the Paris law. So that's one main part of this talk. The other aspect is the metals people, again following on to the Delft group have been real pioneers in this. In 1970, they proposed the Hartmann-Schreiber modification of the Paris law. That's this equation, little delta K here is given by this equation. So they've expanded the Paris law, and notice they've introduced a threshold value. Obviously, the threshold value is the value below which no crack growth occurs. So they introduced that term. They also introduced the denominator here. They've got Kmax entered, and they had a constant A1. A1 essentially is the fatigue equivalent of this quasi-static value, Kc. So this is the Hartmann-Schreiber modification of the Paris law. And it's more than a simple modification, because the metals people, it's nice, we should go into the metals fatigue man. It's really nice work with the metals fatigue man. And they are somewhat ahead of us, as you'd expect, with metals being around for a century or so more than composites and adhesives. And they have the NASGRO method, which is fully validated by both NASA and the Federal Aviation Authority. And essentially embodies, slightly more complex, embodies the Hartmann-Schreiber equation for metallic airframe structures. And they use this to actually predict life prediction and design and fleet maintenance of metallic aircraft. And it can predict R ratio, very short cracks, which is a real problem, and it gives low values of alpha. If you have a high value of alpha, it means, of course, that small change in the load, you get big DADN value, and the crack runs away with you, and your predictions really are pretty useless. So that's the background. So what we're going to do now is, we've said we can use delta root G, so we're now going to take delta root G, plug it into the Hartmann-Schreiber, and we end up with this one. So this is the same as the metals people, just in terms of delta root G, analogous to the Paris law. So here's the value between the maximum minimum loads, square roots of course. There's the threshold value. There's that denominator, G1 max. A is equivalent to the G1C, the quasi-static fracture. To get the threshold, we like to measure it, as we've seen in papers in this TC4 session. It's not always easy. So we decided we'll adopt again the metals ASTM definition of extrapolating to 10 to the minus 10 meters per cycle if we actually can't measure the threshold. So this is the main output of the theory I'm going to talk about. The Hartmann-Schreiber modification using delta root G as the parameter. So if we look at some basic data, here's some DADN data for adhesive joints, obtained actually by myself and some colleagues some years ago. We then use G1 max. What I'm showing here really is 5 replica tests, and just notice the scatter. This is the classic DADN G1 max. At the time we thought we were doing the right thing. All the failures, by the way, are cohesive failure in adhesive. There's no deflational failure in this talk. Thank you. So I've now replotted it with the Hartmann-Schreiber idea. Threshold, G1C basically. This is the Hartmann-Schreiber plot. Notice that all the tests really collapse rather nicely in one straight line. Coefficient of variation is 0.95, so it's quite nice. The slope is 2.55, so it's not like the 9, 10, 20s you see when you use the alternative methods. So it goes a very nice plot. If you look at the data we need in the Hartmann-Schreiber, then these are the values of D, N, notice that these are constant. What varies is the threshold. So in that linear plot, the threshold varies. It's hard to be measured experimentally or extrapolated, as I said. And it can really account for the scatter, as you see. So it's this threshold that accounts for the scatter. One thing you can do is to put this number back and predict these plots. You might argue that's not terribly exciting, because that's where we started. But it just shows you can recompute the basic raw data. As I said, not terribly exciting. Now in adhesives, you often see mode 2 failure. So what happens if we get mode 2? One of the nice things about this work, by the way, we didn't do one experiment. We've taken all the experiments from literature and just reinterpreted people's data. This comes from 1988. This is a different structural adhesive, bonding aluminium alloy. It's mode 2. Notice they've varied the temperature. They've varied the R ratio. These are plotted against delta G, just the simple range of the energy release rate in mode 2 now. A series of lines. The plots have actually come to Hartmann-Schreiber. If we use the Hartmann-Schreiber, which I'll show in a second, we can end up with the computed lines, which you'd hope to, of course. But if we do use the Hartmann-Schreiber, sorry, this is the mode 1 data, just to show first. This is mode 1, show the mode 2. So DADN against delta G again from a different group of authors, same adhesive system. So here's the mode 2, so mode 1 is a function of humidity. If I put all that data together using Hartmann-Schreiber equation, which is here, Notice that we get one master relationship, slope of 2, really nice. Here's the mode 2 data, different test temperatures, different R ratios, and there's the mode 1 data as well, colour points at the 2 humidities, and we get one unique master curve. So it really is neat, and I think that's because the way the Hartman-Schreiber equation is formulated. So we just end up with one master relationship, which is really nice, I think, for engineers. And the slope is very low, the slope is 2, so we can actually use it, which implies we can use it for design work. I said if that slope's 9, 10, 12, as you get with delta G or G1 max as your abscissa there, then it's hopeless. So Hartman-Schreiber, where we've got the range of the stress intensity, sorry, the range of the factor of the energies, the energy release rates, square rooted, there's the threshold, there's the maximum energy release rate in the fatigue test corresponds to the maximum load, and A, if you recall, is essentially G1C or GC from the relevant quasi-static test. The other interesting thing is, can we actually use this for fault prediction? We've shown it works well in the sense of giving us a nice engineering approach. Can we actually use it? Well, aircraft are often repaired using adhesive bonds. This is the GFRP nose cone. It's actually off of British Airways 767. We don't think about this. It's hit by lightning. Plane landed safely, of course, as they do. They're designed to be hit by lightning at times. This is the repair pack that's been glued on. This costs tens of thousands of pounds. They don't throw it away, they repair it, use it another day. Can we predict repair work? That's the thing fatigue. What we've done, this comes from John Allen Pascoe's master's thesis, which he makes nicely available online. Thank you, John Allen. Here's what he did. He took a glare. If you're not familiar with the glare, it's just thin layers of aluminium and thin layers of adhesive, again developed by the Dutch companies. Here's the main sheet. There, imagine this is damaged. We've bonded on a repair sheet of aluminium and then put a doubler plate on top, scarfed it to reduce stress concentrations, and this is where the crack is going to grow. So the crack's going to grow in the adhesive layer where the bonded aluminium plate is repairing the underlying glare sheet. And then we're going to fatigue it. Now what we've done firstly is to calculate the energy release rate as a function of the theoretical crack length. So we put theoretical cracks in, used FE and calculated the energy release rate for 2 stress levels, which are going to be our maximum stress levels, or more accurately, Alan Pascoe's maximum stress levels in his fatigue cycle. So we know the energy release rate theoretically as this crack grows at 2 maximum stress levels in the subsequent fatigue tests. That's the first stage. The next stage is to look at the data, slightly busy slide, but this is the crack length against the number of cycles. Just say look at 150 megapascals, 170 works equally well. These are John Allen's experiments. He carefully measured the crack length against the number of cycles from both sides of the sample. So we had 2 measurements. A look at the scatter as you'd expect between the 2 measurements, they're the points. We then took the mode 1 data, which we found from the literature, fitted it to the Hartman-Schreiber equation, it was LEFM, then combined it with the Hartman-Schreiber equation, and then without any further fitting factors at all, we can actually predict A versus number of cycles. And this is using the mean value of the threshold, which was measured by the authors. They measured a range of thresholds. So if you put the range of thresholds in, that's the upper and lower lines now. This is the, so to speak, the scatter that we theoretically predict. So you can see the theoretical predictions agree very well with experimental points, both for 150 and 170 maximum fatigue stress in the cycle. And more than that, the theoretical work actually encompasses the scatter band rather nicely. So we can predict the results and the expected scatter. And we think that looks extremely exciting. And in the paper, we've done it for 2 different repairs from another group. Have also done repair work. We find the same very good predictions. So to conclude, we get a master linear relationship using the Hartman-Schreiber equation. The slope is relatively low, so we can actually use it for design, just as the metals community can. We can compute, as you'd expect, the basic curve, and the Hartman-Schreiber equation can account for R ratio, mode mix, and test temperature, and yields a unique master linear relationship which captures all of these effects onto one curve, and we've shown that we can use it certainly for laboratory repairs so far, hopefully not the real thing in the future, where you can predict fatigue life of body repairs, where these cracks, I meant to emphasise, go from very short cracks. These are very short cracks of a few hundred microns only.